Hello and welcome. This is A Graduate Student's Guide to Applied Statistics, a course designed to take you from foundational principles all the way to applied experimental design. I'll be your guide on this journey. We'll start with Part 1, the essentials. Before we dive into complex formulas, it's crucial to understand why this all matters and what the ultimate goal of our research is. Slide explaining the goal of research and the two types of statistics. At its heart, research is about moving from simple observation to a deeper understanding. This course is designed to build a reliable bridge from what you can see to what you can infer. To do that, we use two main branches of statistics. First, descriptive statistics, which is all about summarizing the data you have in front of you, and second, inferential statistics, where we use that data to make educated guesses about the wider world. Now for the single most important rule in all of research. Remember this: the design of a study is more important than the analysis. A badly designed study, like a building with a flawed foundation, can never be saved, no matter how brilliant the analysis is. But a well-designed study that was poorly analyzed can always be reanalyzed. These 6 modules of the course, so let's get started. Here's our roadmap. We'll begin by describing and visualizing data, learn the language of probability, and build the bridge to inference. From there, we'll tackle the hypothesis testing framework, cover the pillars of experimental design, and finish with a practical case study on t-tests.
This brings us to Part 2, the basics. Here, we'll build the solid foundation every researcher needs. Slide showing normal and skewed distributions with mean, median, and mode. First up, we need to understand the center of our data. We have 3 key measures. The mean, which is the simple average and works best for symmetric data. The median, or the middle value, which is perfect for skewed data because it isn't affected by outliers. And the mode, which is the most frequent value and is typically used for categorical data. Let's think about what are they differences. After we understand the center, next we look at the spread or variability of our data. First, the range is the simplest measure, but the most important measure of spread is the standard deviation. Think of it as the average distance of each data point from the mean. A small standard deviation means your data is tightly clustered, while a large one means it's spread out. To make your data more visible, a picture truly is worth 1,000 data points, is always truth. 2 essential tools are histograms, which show you the detailed shape and distribution of your data, and box plots, which are fantastic for comparing distributions between different groups and quickly identifying any outlier. Now, there are many software can make nice histograms and box plot easily. Slide showing histograms for 1 sample and 2 sample t-tests. And here's a key point. Visualization isn't just for your final report. It's a critical diagnostic tool. Before you run any statistical test, you should look at your data to see if it meets the test's assumptions. These charts, for example, help us see if our data is roughly symmetrical, which is an assumption for the t-test. Again, there is many available software can assist you to visualize your data. Now we move to Module 2, introducing probability concepts. Probability, the language we use to quantify uncertainty. The core concepts are simple. An experiment is an action with an uncertain outcome, like flipping a coin. The sample space is every possible outcome, in this case heads or tails. And an event is the specific outcome you're interested in. The slide you are seeing showing the normal distribution curve with the empirical rule percentages. Normal distribution curve with the empirical rule percentages. This leads us to the most important distribution in all statistics. The normal distribution, or bell curve. It's symmetrical, and its properties are very well understood. A very useful shortcut is the empirical rule, which tells us that for any normal distribution, about 68% of the data falls within 1 standard deviation of the mean, 95% within 2, and 99.7% within 3. Slide illustrating the central limit theorem, in short, CLT. Module 3 is our bridge to inference, and it's built on one of the most amazing ideas in statistics: the central limit theorem. Here's the core idea. No matter what the original data looks like, if you take many large enough samples and plot their means, the distribution of those means will be approximately normal. This is the magic that allows us to use the properties of the normal distribution to make inferences about our data, and it generally works as long as our sample size is 30 or more. Slide showing the t-distribution formula, but what if we have a smaller sample, or we don't know the true population standard deviation. We use a close cousin of the normal distribution called the t-distribution. It's similar, but with slightly heavier tails to account for the extra uncertainty. In real research, you'll use this constantly, because we almost never know the true population parameters.
Part 3. The application. Okay, we've built the foundation. Now for Part 3, the application, where we take these concepts and use them to conduct our research. Slide introducing hypothesis testing. Hypothesis testing is the formal process we use to make decisions with data. It always starts with two competing hypotheses. The null hypothesis is the skeptic's view. It assumes there is no effect or no difference. The alternative hypothesis is the researcher's view. It's the effect you are hoping to find. Slide explaining the p-value and significance level. So how do you decide between them? The null or the alternative? We use the p-value. The p-value is the probability of seeing your results if the null hypothesis were true. We compare this to our predetermined significance level, usually 5% 66. The rule is simple. If the p-value is less than or equal to our significance level, we reject the null hypothesis. Slide illustrating type 1 and type 2 errors. But this process isn't without risks. There are two types of errors we can make. A type 1 error, or a false positive, is when we reject a true null hypothesis. The risk of doing this is equal to our significance level. A type 2 error, or a false negative, is when we fail to detect a real effect. It occurs when you fail to reject a false null hypothesis. In simpler terms, it's a missed opportunity. Slide illustrating statistical power. This brings us to statistical power. Power is the probability of correctly detecting a true effect. If your study has low power, you are likely to miss a real finding, which wastes time and resources. As a rule of thumb, we always aim for a power of at least 80%. Slide showing the cycle of theory, prediction, experiment, and observation. All of our tests rely on good data, which comes from good experimental design. There are three pillars to a strong experiment: randomization, which eliminates systematic bias; replication, which means repeating treatments to ensure your results are reliable; and blocking, where you group similar experimental units to control for known sources of variation, like testing on different days. Slide explaining the difference between independent and paired samples t-tests. Let's put it all together with a t-test. The core question a t-test answers is, are the means of two groups significantly different? The critical distinction is knowing what kind of data you have. If your two groups are completely separate, like a control group and a treatment group, you use an independent samples t-test. But if your scores are linked, like in a before and after study on the same people, you must use a paired t-test. Slide with a research mind map. The key takeaways for the research. So to recap the entire process, we start by describing our data. Then we use the principles of probability to infer, which allows us to test our hypotheses and finally make a decision. Always remember the critical link. Your experimental design determines your statistical test. So plan your analysis before you collect your data. Visualize your data first, understand your assumptions, and focus on designing robust experiments.
That concludes the main presentation. I'd now be happy to answer any questions you may have. The final conclusion slide with 4 bullet points to leave you with the most important takeaways. First, strong foundations are essential. These concepts are the bedrock of all valid analysis. Second, design dictates analysis. A robust design is the only way to get data you can trust. Third, the right tool matters. Choosing the correct test is critical for accurate findings. And finally, the goal is credible research. These skills empower you to create evidence-based conclusion.
Thank you very much for your attention.